There's actually a phenomenon called pit wear, where two bones rub together over time. So you might look at something like, oh, this is a really gnarly bite mark. This is so awesome. It's like, oh, no, wait, this was just a femur that was rubbing against somebody's jaw, and that's why it looks like there's a bite mark there.
Welcome to Science for the People. I'm Bethany Brookshire, science writer at Science News and Society for Science and the Public. Until you break one, you might not spend much time thinking about your bones. But they are wonderful, living scaffolding on which we are built. Scientists spend lots of time looking at bones, using them to figure out how we evolved, how we get sick, and how and when people spread out over the world. But these skeletal studies are not without controversy, and not just scientific controversy. Here to, as it were, flesh out the bones of the topic, is Brian Switek. He's a freelance writer and author of My Beloved Brontosaurus and Written in Stone. Now, he's got a new book, Skeleton Keys, The Secret Life of Bone. Welcome, Brian.
Well, thank you so much for having me on.
Now, you're, as we can tell from your previous books, Written in Stone, My Beloved Brontosaurus, you're a paleo person, and your previous two books were about animal fossils, especially dinosaurs. What made you want to look at the very modern human skeleton?
Well, I realized that I wasn't really paying very much attention to my own skeleton, or human skeletons in general. I kind of had this almost cartoon version of what I thought skeleton looks like in my head. Like I knew, there are upper arm bones and lower arm bones, but at the end of them, who knows how they connect to each other? I don't really know. So as much time as I spent, looking at, a lot of these, prehistoric monsters and other things that I love so much, I realized I wasn't really looking at my own skeleton very much. I didn't really know how everything came together, how it formed. And when I realized that, I thought about, well, what if I applied the same questions that I applied to fossil animals to ourselves? So I've written a whole book. You mentioned My Beloved Brontosaurus. That was about updating the science of what we know about dinosaurs and their biology, really going back to the skeletons. Like the bones have been the same as they've always been, but our interpretations of them changed, and a lot of the questions that we ask have changed. And I'm pretty familiar with doing this. I've done this over the past 8 years, out in the deserts of Utah and other places in the American Southwest. And I'm hiking around and getting sunburned, bitten by gnats, dehydrated, the whole deal. I come across, a piece of bone, and I immediately wonder, like, okay, what bone, what element of the skeleton is this? Is this a dinosaur? Is this another animal? What part of the skeleton did that belong to? What did it do? What muscles were attached to it? How did it move? So basically from even like a scrap of a fossil, we ask all these questions about the identity of the creature, what it looked like, what its behavior was, and all this stuff it's pretty standard stuff for paleontology because we can't look at the living animals in most cases. So I thought about applying that same logic to humans and to our skeletons. If I took sort of the paleontologist approach to the human skeleton, what stories would come out of it? So I just kind of started tugging at that thread, and Skeleton Keys is the result of that story.
During the whole time you were writing the book, did you end up singing to yourself, the knee bone's connected to the thigh bone?
Only occasionally. And, we'll get to it in a little while, but the knee bone is not connected to the thigh bone. It's actually super, super weird. And that's one of the things I loved about this process is like, I didn't really know what the knee bone connected to. And it turns out that as far as bones go, it's not really connected to anything. And that's one of the wonderful things about this is like, we kind of take our skeletons for granted. And oftentimes when we see them, especially in depictions of pop culture, I see death metal album covers, Halloween, like the only like positive association is the Day of the Dead, and Coco was a wonderful film as well that played with this, obviously playing on the holiday. But most of the time, bones are treated as pretty grim. You see them on poison labels, or the Jolly Roger, flying from the pirate ship's mast and all that stuff. But they're really these living things inside. It's living tissue, just like your skin and muscle are. Yet we kind of take it for granted. We think it's static and kind of boring. So that was the other sort of inspiration behind this. It was, thinking of bones as living things, as evolving things, and things that record our culture, these sort of time capsules, these dynamic things that respond to the environment, respond what we do to them, and respond even to the human culture, that we can sort of record what was happening, in our lives that wouldn't otherwise make it into the record at all. So, aside from taking the paleontologist's view of this, it was really trying to really drive home this message that, bone doesn't have to be the symbol of, death and the afterlife, that it really is this vital structure.
So speaking of vitality, it's true. I mean, we know that bones are alive. They do heal when we break them most of the time. Can we start with bone basics? What is a bone? Like when we are looking at a live bone, what are we looking at?
Yeah, well, that's what's kind of confusing in a way about the terminology of bones, or osteology is the study of the science of bones. That bone is a tissue. It's a tissue type. So you have your bones like an element. So usually if we say like your humerus, that's your upper arm bone, or your femur, that's your thigh bone, that these things they're bones, but they're specific elements as part of the skeleton. They make sense in the context of the whole. But bone itself is a particular tissue type that's mostly made of two materials. There's collagen, which is an extremely common protein in your body, and bone is like 90% collagen, so it makes up most of it. And then there's the mineral part, the hard part, called hydroxyapatite. And even though it's a very small percentage of the actual bone tissue, it makes up about 70% or so of bone weight. And those two things together make bone what it is. It makes it durable and flexible. It makes it a really resilient material, and this tissue that is alive. I'm sure we'll get into it in a minute, like all the little cells that do all the bone work, building things up and breaking things down and changing them. But you go to a museum and you see a human skeleton or a dinosaur skeleton or a fossil mammal skeleton. Each of those bony elements, each individual bone is made of specific bone tissue. And technically speaking, you can have skeletons that aren't made of bone. Like sharks and rays, for example, have skeletons made of cartilage. So their elements are not made of bone, even though they have skeletons with many similar parts as us. So when we talk about bones, we're really talking about the specific bone tissue that's made of these two elements. And what I kind of love about it is you can get a feel for at least the flexibility that's in bones by doing a very simple at-home experiment. I remember this from my elementary school science class, where you would take a chicken bone, or really any bone from your lunch, depending on what you're eating. My apologies to anyone who's vegetarian or vegan out there. But if you have a chicken bone, you can put it in vinegar for a while, they say acetic acid, and the mineralized part of the bone will dissolve away. And you're able to basically tie that chicken bone in a knot, and that's the collagen that's left. And it shows, it still looks like a chicken bone. It still maintains its shape because bone is mostly collagen. But you take that mineralized part away, and bone is incredibly flexible. It's too flexible. You can't really do very much with it. By contrast, if you took all the collagen out of a bone, it'd be extremely brittle and extremely easy to fracture. So it's really kind of amazing that we have these two, biologic compounds that in combination make bone both super strong and very resilient. And that really opened up a ton of evolutionary possibilities. Like, I mentioned early on in the book, it's kind of amazing that bone is the basis for the largest animals that ever lived, in the ocean, the blue whale, which is still alive today. And, in the fossil record, dinosaurs like Supersaurus that got to be over, 110 feet long and weigh in excess of 40 tons. And it's also the basis for tiny, tiny, tiny vertebrates, like these little salamanders that could basically fit inside of a raindrop. They're so little, but they still have bony skeletons inside. So it's just really opened up this amazing array of evolutionary possibilities in terms of body size and body shape, because it's such a good, for lack of a better term, building material.
Well, I have to say, first off, your elementary school science projects were way more awesome than mine. And I am going to grab a rotisserie chicken this weekend and put it in vinegar because I want to try this.
Yes, tie a chicken in a knot. It'll be fun.
I'm very much looking forward to my weekend. But, you mentioned that we have this collagen and we have this, you're going to have to help me, hydroxyapatite. Hydroxyapatite. It's like a really hungry hydroxyapatite. Cool.
There you go, yeah.
So we have these two, and when you kind of look at a bone, you don't really think that there are cells there, but there are cells there. What are the cells in there, and what are they doing that makes bone so living and dynamic? It's not just this kind of combination of those two things.
That's right. So there's a whole series of bone cells that are constantly active. They're doing stuff right now. It kind of makes my skin crawl a little bit to think about it, especially because there are cells I'll get to in a little more detail in a second called osteoclasts, are kind of like these Pac-Man type cells that resorb bone. So as bone is being laid down, they're also resorbing it at the same time. And if I just sit there, it's kind of weird to think about all these little cells like all over in my body reshaping my bones as we speak. There's actually a way to time the turnover of bones where, it's a certain number of years that, your rib bones basically turn over completely. It's not all at once. It's not like you get a fresh new element there, but basically that's the amount of time it takes if you calculate, how long it takes to lay down new bone and resorb bone for, bones to basically remake themselves. But the basics of this is, so bone formation, you have these cells called osteoblasts. And these are basically the cells in your bones that are responsible for bone formation. And they'll make this lattice work. That's basically the structure on which new bone is built. And it's not made of bone material just yet. But like once that sort of framework is in place, then it begins to ossify. So basically it's these little cells and they build these walls around themselves, and the cell inside switches roles as the bone tissue mineralizes and forms, and they basically regulate the growth of some of the growth of bone after that. They don't completely die, but they take a more subdued role. So that's forming constantly. At the same time, you have osteoclasts, and those are the Pac-Man type cells that are constantly resorbing your bones and changing things. And while these two cell types are in balance, your bones grow pretty normally. But osteoclasts, basically if you have not enough osteoblast activity or too much osteoclast activity or both, that's when you get things like osteoporosis when your bones start to get brittle because they're not maintaining themselves as well as they used to. So this is the sort of basic maintenance crew that not only forms your bones as when you're developing, when you're an infant, and basically gives you your initial skeleton that starts to fuse. They're responsible for you getting to your adult height, the daily day-to-day maintenance of bone. If you break a bone, these are cells that are also responsible for some of those repairs. It's like the growth is also the built-in repair system, and it's also responsible for some of the things that go wrong with their skeletons, especially in older age. So these are cells that have specific duties, but depending on how they're regulated, it makes the difference between whether you're growing up like a weed as a teenager or if you're starting to shrink in old age.
And one of the things I found really interesting was you talked a lot in the book about the evolution of skeletons and the evolution of bone. And I knew this, I guess, but it kind of is weird to think about it, that the first thing that happened was a spine. And the spine happened even before a brain case. Do we know why the spine happened first? Why is the spine so important?
Right. So you mentioned a spine, and the creatures that we see, basically the forerunners of the spine so these early spines weren't like our backbones with these stacked vertebrae. It was a predecessor called the notochord. And you can see this in some animals today called chordates, things like tunicates and sea squirts that don't look very much like it at all. They basically look like living plastic bags that live on coral on the seafloor. But they're relatives of ours because we are joined by this particular structure. And we see this start to appear during what paleontologists know as the Cambrian explosion, maybe a little bit before. But amongst these little sort of proto-fish, like squiggly little animals, they're very, very short. They're shorter, in most cases than the length of your little finger. And, they don't have bone tissue. They don't have mineralized bone tissue like we do, but they have this sort of toughened rod running through their back, basically on the upper side of the body, what we call the dorsal side of the body. And that became the forerunner of our spines. That basically determined where the spine is going to be. And we're not sure entirely why that came first. It certainly had a biomechanical function, like surrounding these forerunners of the spine. You see these sort of either W or sort of V-shaped little notches in many of these fossils because they're often found in places of exceptional preservation, like the Burgess Shale in Canada or the Xinjiang deposits in China. And those are muscles. They're called myomeres. So basically, this was a site that was getting toughened up for muscle attachment to allow these little protovertebrates to swish around from side to side and move through the water and hopefully, evade all the, invertebrates with the, gnashing and grasping and clawing mouth parts that were dominant during that time. And this is important because, even if we're still figuring out, why that notochord first evolved, the fact that it's along the back really set up the basis for our vertebrate body plan. It didn't have to be there. It could have very well evolved along the stomach side or maybe off to one side and not another. So this is just sort of a quirk of history that because of that set something about the vertebrate body plan sort of not in stone, but set it in such a way that everything else now has to be arranged around that. So that's why our backs are at our back and not our fronts or some other arrangement that we couldn't otherwise conceive of. And the fact that these protovertebrates, we can look into the past now, we can look back 500 million years and more and say that, okay, these are close relatives of ours and these are our ancestors. But at the time that wasn't apparent. These animals were not dominant at all. They were very, very rare parts of the fauna that they appeared in. There was no indication that they were ever going to become successful or dominant in any way whatsoever. For a while, it was thought that there was a mass extinction event at the end of the Cambrian period that basically wiped out a lot of the super weird invertebrates. Some of my favorites, like Anomalocaris, this thing that had these two grasping great appendages sticking out of the front of its head and this shutter-like mouth and bug eyes and big flapping flippers on the side of its head. The biggest ones are about as big as you and I are. But things like that were the dominant animals at the time. And it was thought that they just kind of went extinct overnight, and the vertebrates went, hooray, and started to proliferate, and you get fish and things like that. It turns out that that's not true, that a lot of these Cambrian weirdos survived for tens of millions of years longer than we thought. So you had this old weird invertebrate fauna, and you have protovertebrates starting to take off and starting to become much more fish-like. And it's a much more, we don't entirely understand it yet. Okay, like how did this happen? It's not a neat and clean story like it used to be, of like the competition goes away and then vertebrates are allowed to take off. You have the vertebrates sort of starting to succeed alongside a lot of these animals that, for lack of a better term, kept them down previously or occupied a lot of this ecological space and didn't let them proliferate. But the fact that protovertebrates had this notochord, had this structure in the place they did, has a lot to say about why we have bodies the way that we do, and the way that the nerves and the nervous system got bundled together, and the sensory organs that they had were all arranged in their head rather than being distributed throughout the body. Even though there wasn't a skull yet, and there wouldn't be for millions of years after them, it means, okay, we're centralizing all the sensory input basically in one part of the body, and it's going to be important to protect it. So all this stuff sets up the later evolution of the skeleton. So you can look at some of these things. You can go to the places, like I mentioned in the book. If you go to the Smithsonian National Museum of Natural History, there's a wonderful exhibit about the Burgess Shale fossils on the first floor. And you can see this animal called Pikaia that I mentioned in Skeleton Keys. And it's, not very big at all. It's pretty teeny. It doesn't seem very interesting compared to some of the animals it's alongside. But this is basically a representative of what our ancestors look like at that time. And if you know what you're looking for, you can basically start to see the resemblances. Like, okay, there's the head with all its, sensory information organized in one place, just like me. And there's the notochord, which is, the predecessor of my back. And once you do that, you're looking at this thing that's 500 million years old, and you can see a reflection of yourself. So, it really drives home the point of sort of this idea of, evolutionary tinkering, that, there are big jumps that can happen through, mutation, natural selection, and all that wonderful stuff that we know that explains, the origin of, whales that lived on land, went to the water, and dinosaurs that became birds and everything else. But if you look for the similarities, you can detect those going way, way, way back. And I think that's kind of cool to be able to look at something that's 500 million years old, this meek little squiggly thing that was probably afraid of everything in its environment, and say like, hey, cousin, I think that's pretty cool.
And this thing that had this, tiny little notochord, which now I'm thinking of what would have happened if that notochord had formed along the stomach area, and I'm going to have nightmares.
Yes, my apologies.
But we had these little notochords. And these notochords, they started out kind of this hardened material. There was cartilage, but there was actually something before bone. Before bone, there was something called aspidin.
Yeah, that's
This
right.
is a totally new word for me. What is this?
Yeah, it kind of blew me away when I learned about it too, because I didn't know that it existed. And it kind of took a little bit of turning around in my head to understand it, because aspidin is a bony tissue, but it's acellular. So we were talking a few minutes ago about the way that our bones form and the way they maintain themselves and break down, and the sort of construction crew and demolition crew of different cell types that exist in our bones. Aspidin didn't have any of that. It's basically like an organic cement. If you find a fossil with aspidin, so many of these are early fish, that have this aspidin kind of coating, crunchy on the outside and chewy on the inside. And that's exactly why they had this particular coating. I know it's close to Valentine's Day, and now I'm thinking of like, oh, could I have like fossil fish that are like chocolate themed?
Chocolate covered cherry fish? Yum.
Yes. But so they had this, tough outer coating as protection because there was still a fair amount of, invertebrates and other critters that, wanted to eat them. But it didn't maintain, it basically just grew. And the closest thing that we have to it is like we have a tissue in our bodies that's part of our modern skeleton that's very much like aspidin. Those are our teeth that, once you get your adult set of teeth in, you can wear them down, but they're not maintaining themselves. They're not growing. You've got, the pulp cavity and stuff inside, and there are soft tissue aspects of it, but the enamel of your teeth, that hard part that you do all your, biting and chewing with, that doesn't change. It's laid down and then it stays the same except for the fact that you wear it down. And aspidin was very much like that. So it's this acellular sort of pre-bone tissue that existed as a kind of armor so basically, bone and teeth were very, very similar at their origin. So you can think of these, little fish that kind of like, if you think of like a Roomba with like a tail coming out the back end, swishing around, if the Roomba propelled itself around your floor with a sort of swishy fish tail, that's more or less what some of these animals look like. And it had this outer covering that was made of this really hard, sometimes sharp, protective acellular material. And that's where basically the beginnings of bone started to take off. And again, I apologize to listeners for more nightmares about being chased by Roombas covered with teeth.
Are you kidding? I'm buying a little pet shark suit for my Roomba. Duh.
Perfect.
It's going to look great. So,
as long as it plays the Jaws theme as it moves around.
Oh, absolutely. Required. Now, you were mentioning that these animals were crunchy on the outside, soft and tasty on the inside, and one of the things I found incredibly mind-blowing was that you explained in the book that bone was on the outside first, before it became an inner skeleton. There was, a notochord, and then you were crunchy on the outside. Where was the bone on the outside, and how did it get inside?
Basically, bones start off as this armor plating on the outside, and sometimes paleontologists talk about our skeletons, our endoskeleton, as a sunken skeleton. That this was something that grew on the outside and sunk inwards. Although that's not quite exactly right. It's not as if these fish grew a arm bone or a tailbone on the outside of their bodies, and then that got slurped inside and incorporated. It's more that once this bone tissue evolved for protection, that basically, through natural selection, you would have fish, at the beginning, they're all soft, squishy things. And one of them might have had a slightly harder, outer body covering. And those with slightly harder outer body covering survived longer or able to leave more offspring because they were harder to kill or to catch, or they had better success at surviving and living a longer life. You do that often enough and you get the formation of this aspidin or this outside armor. But once that happened, basically bones started to show up in other parts of the body. That the spinal column, basically the notochord, started to become mineralized. Same thing with that sensory center within the head, basically the forerunner of the skull, because you want to protect all that stuff and give it a casing. So that basically once bodies evolved to form bone, the exact pathways by which this happened are not entirely clear, but I mean, we see this in some of our own skeletons, which, we may get to later, that you can grow bones in all parts of your body. Bone is a tissue that's in your body, and sometimes based upon injuries, people can grow bones in places where they wouldn't expect. People have grown bones in their salivary glands. People have grown bone tissue in their breasts or in their genitals or in other places where you would not expect bone to be, because you just need the right combination of sort of calcium salts and the right conditions to make bone grow there. So something like that probably happened in these creatures, that once bone formed, that there were other pathways by which it started to form in the skeleton, just as an accident, but it turned out to be adaptive. It turned out to add a little bit more strength to that backbone, add a little bit more harder muscle, a little more muscle attachment, so you can pump a little bit harder with that tail as you swim, or form around the sensory organs in the head, forming a skull, and adding a little bit more protection, a little bit more resilience. So really, once the accident of bone happened, there's all kinds of sort of variable pathways that opened up, and bone started to form inside the body, and eventually that outer skeleton, that outer armor, kind of fell out of evolutionary fashion, that there are other ways to evade predators or protect yourself. Or, there are compromises that were made where if you're basically living inside this bony box, like, the swimming turtle kind of creature with the fishtail, hanging outside the end of it, you're not very flexible. You're relegated to certain kinds of life. Your speed might be impaired because you can't swim with the whole body. You're basically the static thing with the tail doing all the propulsion for you. So there are other variations that opened up once, bones started to come inside, strengthen the inside of the body, and start to disappear from the outside of it. So this, period, in the age of fishes, that there's a sort of evolutionary experimentation going on, or this variability, and you start to get all these different forms so bone didn't just have to live on the outside. It actually provided biomechanical and protective advantages on the inside as well.
And you mentioned it kind of, the outer bony plate concept kind of fell out of fashion, very 80s, not now. Are there any animals that have stuck with it? Are there any animals that still have that outer bony plates or anything?
I mean, the closest thing that comes to mind is not in the same way, but are turtles. And turtles are super duper weird. If you ever go to a museum and they have a turtle skeleton on display, especially if it's one where they have basically the turtle skeleton displayed on its back, or have cut away the bottom part of the carapace so you can see inside the skeleton, their shoulder blades are on the wrong side of their rib cage. They're inside. We don't know quite how this happened. Paleontologists have been studying this through the evolution of turtles, but these are animals that they live inside of a bony shell, and it does add some limits to their mobility. They're protected, and some species, like one of my favorites when I was a kid was the box turtle. To just see it draw its head in and then close that little flap to kind of throw shade in a reptilian way at whatever predator is coming after it. But that's the closest equivalent today. There aren't fish anymore that are quite like this, because a lot of these fish were also jawless fish. And basically what they had for a breathing apparatus, for a feeding apparatus, was just a single hole that basically, like, whatever they would, swim through an algae bloom or through a cloud of plankton or something like that, and basically suck in whatever. Maybe there were soft tissue structures that allowed them to open and close a little bit more, but they didn't have jaws. They didn't have a mouth as we think of it now. And the bony plating was part of that. If you basically have a face that's entirely bony plate, there's not a lot that you can do with that if you don't have a hinge, if you don't have a jaw. So that's part of the reason why this fell out of fashion. There actually was an extinction event that happened, and it's thought that a lot of these jawless fish, sort of the only representatives today, and they're not bony at all, are lampreys and hagfish, that were these sort of bottom dwelling species, and something about the oceans changed in terms of oxygen content or how nutrients are circulated. And basically there's something that put the jawless fish at a disadvantage, and jawed fish, which had evolved by that time, were able to take off. So I think if we're thinking about animals that live inside a bone box, turtles are probably our best example, but there's nothing quite like those early ancient fish that is swimming in our oceans today.
Now, you mentioned that, some of the animals that we're talking about, they have skeletons, like turtles, for example, but a lot of fish have skeletons made of bone, but there are also successful species that have cartilage instead, like sharks and rays, and obviously that's kind of a successful mechanism. They've been around a really long time. It kind of made me wonder, why are we bone and not cartilage? Because yes, collagen is super flexible, but I mean, if you've, touched a shark, those things are tough. They can, obviously the cartilage is getting them places. Why is bone better? Why are we bone and not cartilage?
Yeah, sharks are pretty hardcore, especially since their skin is basically teeth. It's just tiny, tiny teeth. And that's why you don't rub a shark the wrong way, because it's basically like getting bitten by a shark, only you're doing it to yourself by rubbing it, from tail to head. Don't do that.
I would argue don't pet a shark. Just don't pet them.
Probably, yes. That'd be much wiser advice. I was focused in too narrowly. Sharks can touch you. You don't touch the sharks. It's unclear why bone became as successful as it was. This is one of these questions it's awesome to ask. It's like, but how do we test it, especially amongst a time period that we can't directly visit? Some of it might just be happenstances of evolution, things that we don't entirely understand. Maybe there was some advantage that came along with bone in terms of, bodily maintenance or response to injury, or the way that certain, fish took up nutrients or things like that we can't directly see or understand, that, made the difference. And there's a bias against cartilaginous fish. Then again, sharks and rays are incredibly successful fish, and they're still with us in many of the forms that have been around for a long time. Incredible variety of animals, and it works very well for them. In terms of why we're bone, a lot of that probably has to do with the biomechanics of living on land and gravity associated with it. That I'm not sure how well a fully cartilaginous creature would do on land, because a cartilaginous bone might not be sturdy enough to actually support weight, especially standing upright like we do. Or, we might not have wound up with giant dinosaurs that we have, because cartilage is very flexible, and it's great if you're in an environment where you don't really have to worry about gravity as much, that you're basically like living in a zero-G environment. That's great. But if you're living on land and you're stomping around, you want something that's a bit sturdier. And bone kind of opened up that pathway, whereas cartilage didn't really do it. And we even see this amongst ourselves, when we're infants and our skeletons are still forming. They're still fusing. Like the ends of our long bones are still cartilage, and they haven't turned to bone or fused the rest of the skeleton quite yet. We're not really great at moving around. And part of the fusion of our skeletons and the growth of our bones has to do why we're able to stand upright and move around and be successful on land. So I'm not entirely sure why so many fish adopted it, but bone did make possible the transition from the water to the land. Whereas if these were cartilaginous organisms, it probably either wouldn't have happened or would have happened in a very different way. And you might have had life that lived much closer to the ground or at much smaller body sizes, because it would have been constrained by the different sort of mechanical properties of cartilage versus bone.
Well, now we've gone through the evolution of bones. Now we're going to talk about the human bones, because this is all about, technically speaking, the human skeleton. And Brian, the first human skeleton that you talk about in your book is from La Brea, as in La Brea tar pits. People think of it as the La Brea tar pits, but that's wrong. La Brea means the tar pits. So if you say the La Brea tar pits, you're saying the tar pits. So don't say that. It's La Brea. I have been there. It's amazing. Anyway, there was a human skeleton found in La Brea. We usually think of it as a place where they find huge dire wolves and mammoths and, awesome animal remains. But there is a human skeleton there. It's called La Brea Woman, but it might not be that simple. Can you talk a little bit about that?
Yeah. So this particular fossil is the only human skeleton that's been found at the La Brea asphalt seeps just yet. And it's a little bit younger in age. So basically, in other words, it came after the extinction of our Ice Age favorites like Smilodon, the dire wolves, and everything else that's found there in abundance. And it's unclear how this person became interred in the asphalt seeps. For one thing, many of the bones, we have a partial skeleton, basically, which is relatively rare in the asphalt seeps. For a very long time, most of the skeletons and osteological elements that are pulling from the tar pits, as well as things like, beetle casings and snails, like everything down to microscopic stuff, it's all mashed up and isolated. That these are all from, animals that got trapped in the tar pits, and they, decomposed, and their skeletons fell apart and everything got moved around, especially since asphalt seeps are very sensitive to temperature and to other things like even, tremors from the seismic activity in the area can kind of move things around. There's actually a phenomenon called pit wear, where two bones rub together over time. So you might look at something like, oh, this is a really gnarly bite mark. This is so awesome. It's like, oh, no, wait, this was just a femur that was rubbing against somebody's jaw, and that's why it looks like there's a bite mark there. So this is very, very dynamic environment in which things generally fall apart. It was really only when they expanded their excavations to make room for a parking lot that they started to find articulated skeletons of mammoths and things like that. So to find a partial human skeleton, including skull and ribs and limb bones and all that wonderful stuff, was pretty weird. And we're kind of unclear whether this was an intentional burial, whether this was somebody who just kind of blundered into an asphalt seep and they couldn't get out. There are all kinds of crazy ideas about how this skeleton got there. But traditionally, the skeleton has been known, in popular circles as La Brea woman. If you go to the La Brea Tar Pits Museum now, you can see artistic restorations of who they believe this woman looked like. And I think there used to be a model that was on display. But like you said, it's not really quite that simple in that there is an osteological fact, and then there's the interpretation of it, because as we all well know, there's a difference between sex and gender. So we often talk about human skeletons in terms of like Kennewick Man or La Brea Woman or Narikotomi Boy, or, we give them basically a gender, and that's based upon what we see in terms of their osteological sex. And that's determined by the hip bones, that basically there's a certain angle of a certain hip bone at the front that if it's relatively narrow, it's much more likely to be an osteological male skeleton. And if it's wider, it's much more likely to be an osteological female skeleton. In the case of the skeleton at the La Brea Asphalt Seeps, it seems to be an osteological female. So it's natural, especially, previous decades of anthropology and archaeology say, okay, female skeleton woman, we're going to restore her in this particular way and come up with, ideas about, who she was and what her role was in society and how she might have dressed and all these things, all the stuff that's based upon an anatomical fact, but don't necessarily follow. We don't know who this person belonged to in terms of cultural affiliation, other than that they were Native American. But we don't know anything about the people who were living in that area of Southern California at the time that skeleton was deposited. We don't know what their ideas of gender or gender roles in their society were. So it was one of those things I was kind of, I hadn't really thought about before. I hadn't examined this myself. I was just like, oh yeah, like I want to go, like when I wrote the email to John Harris, who was a curator at the time, to go look at the skeleton, I said, I'd like to go see La Brea Woman. I didn't give it a second thought. That's just what we called the skeleton. It was only really when I started thinking about it, it's like, wait a second, like, okay, based upon the hip bones, which is the one reliable indicator, we know that this person was an osteological female, or at least consistent with what we would expect with that. But all this other stuff that we've built on top of it, we don't really have any idea of, and we might be giving a false image to the public of what we know and how we know it by basically taking this one data point and then blowing it out into this wider interpretation. I think it's important to really highlight and say, like, when we don't know something, or when something is based upon, an educated guess or a hunch, or, this was a person and they had, muscles and soft tissues and guts and all that wonderful stuff, that we know comes biologically along with being a person. But in terms of their culture and their identity and who they were, we really don't have any idea.
But you did mention DNA testing. How much can DNA testing clear this up? Are there limits?
Yeah, so actually the skeleton from La Brea is an excellent example of that, because in order to do DNA testing, basically in order to prepare the skeleton for that kind of testing, it would take a sort of cleansing process that would destroy the DNA and leave nothing left. So basically getting the tar out of the bones and making this a viable specimen to do testing on would destroy the DNA in the process. Now, maybe in the future, someone will come up with something that will change that, and we can do that. But DNA testing is not always possible on these bones. And one of the things that is important to remember about DNA is that it starts to degrade at death, and it actually has a half-life. And I think the half-life is such that really, if you're looking at deep time, like, and dinosaurs come into play here, like, this is one of the reasons why we can't have a real life Jurassic Park, because DNA degrades at such a rate that even under ideal conditions, like let's say a cold, dry, like refrigerator, like cave, fragments of DNA will only exist for about 6 million years or so. And even that'll just be like the last tatters as it, erodes away. So that's not even near anywhere close to getting back to, Triceratops or T-Rex or anything like that. So when we're looking at some of these, ancient skeletons, like amazing work has been done with, for example, reconstructing the Neanderthal genome and discovering, whole groups of people that we didn't know existed before, like the Denisovans. Things like that, are wonderful, but they're also pieced together from many different sources and based upon a hypothesis of what a complete genome would look like, because it's impossible to get a complete genome because the DNA has been degraded over time. So there are limits to what we can learn. Like, DNA is not going to be a silver bullet for whatever question we might have, especially as we go further and further back into human history.
You talk a little bit in the book about phrenology. which is that pseudoscience of feeling the bumps on your skull and saying, I see your creativity bump is very large. You are obviously a creative person. And, we think of that now. It's descended. It's a pseudoscientific joke. The idea that you can conclude anything about someone based on the shape and size of their skull, other than whether or not they've been hit over the head with a hammer. You can probably conclude that. But
like, you must be Phineas Gage.
There's a hole here. But yeah, the idea that we can conclude anything about anyone's personality or intelligence based on the shape and size of their skull is ridiculous. But while we might laugh at that now, you actually pointed out, and I was very surprised. In retrospect, I should not have been surprised to learn that phrenology was used to support some really horribly racist policies. And in particular, you talked about the work of Samuel Morton. Can you talk a little bit about that?
Yeah, so I mentioned, Morton wouldn't have described himself as a phrenologist. He did have a prominent phrenologist sort of endorse his work in the first book that he came out with. But I connected the two together because it had something to do with the emergence of anthropology as a science and the way that it was being done. And so Morton worked in the early to mid 19th century, and his main deal was, collecting skulls to figure out what the divisions of races were amongst people. So basically, if you could take certain skull measurements, and he was particularly interested in the capacities of skulls. And he never said this explicitly in his published works, but the general idea was, like, if you have a bigger skull capacity, you have a bigger brain, bigger is better, therefore you're more intelligent. We know that this isn't true, but this was the idea at the time. And this didn't just come out of nowhere. He just didn't invent this out of nowhere. Prior to Morton's work, and one of the reasons the phrenologists sort of endorse his work is you had this idea of, that there are certain organs in the brain. We know that there are certain parts of the brain now that we label, all kinds of neat things, like the hippocampus and the amygdala and all that neat stuff. But this wasn't that. This was saying, like, you have an organ of covetousness, or you have, an organ of righteousness in your brain. Depending on the size of that, your brain will kind of be enlarged or swollen or shrunken in different areas. And because the skull fits very tightly to the brain, that by looking on the outside of the skull, you should be able to find, like, where those enlarged or shrunken areas are, figure out, like, what those, based upon that map of what the brain areas should be, why someone's behavior is a certain way. And this was thought to be, a good science, that you were taking measurements, you were looking objectively at something that could be measured and compared. Where, and this to some, or at least in pamphlets and some literature at the time, was passed around as like a social justice kind of movement. Because previous to this, if somebody did something terrible, they committed a murder or something like that, it might be like, well, the devil made them do that. And the guy who might be innocent might say, well, I didn't do that. And they'll say, well, you're lying because the devil's making you lie. And it's like, you can't argue against that. And there's a lot of, sort of injustices that were committed because of this. And phrenologists, part of their sales pitch was kind of like, well, we can do away with that. We can look at the head of this person and say, like, well, their murder organ isn't big at all, so they couldn't have possibly done it. Or at least they're trying to, like, get at a different understanding of behavior that was based in nature. And that was the kind of general idea. And a little while ago, phrenology kind of went through a little bit of an apology tour. Not that it was good science, but it's like, well, this is the forerunner of maybe some modern neuroscience, like organizing the different parts of the brain, do different things. And it kind of primed the academic community to accept a different idea about how the brain worked. But as I did my research, a lot of historical research, people who've read the biographies of and the literature of the people who were prominent in this movement and what they did. Mostly they were super proud that they had a science that was all their own, and they had an expertise that was all their own. Were really defensive about that and making their living through that. They didn't want copiers or imitators. And on top of that, that you could use it for either for good, to argue that, okay, like, stop blaming like demons or possession or other things for people's weird or bad behavior. It actually has a biological cause. But on the other hand, people saying, taking these measurements, especially as phrenology like spread out from Europe into the areas that were still under colonial rule in a lot of parts of the world, and say like, well, of course these people are meant to be dominated by us because the organs of their brain and their head are much smaller, they're different from ours, and we're clearly superior and they're clearly inferior. So it was a way to basically try and collect data to suppress people. And they weren't actually getting data that meant anything for this. It was just they were coming in with a preconceived conclusion about how life should work, and they're supporting it with what they felt were new science. So Morton was kind of the next step in this. So he wasn't, even though he wasn't necessarily a phrenologist, he was taking skull capacity measurements and trying to divide races of people based upon those, and the implicit assumption that even though he didn't make it, that bigger brain capacity was better. And surprise, surprise, it was white people who had the biggest brains of all. And basically this was used like, people who were pro-slavery, leading up to the American Civil War, people who, wanted to continue to maintain their power, basically use it. So like, look, we have the data now that this is how like the natural order of things should be, when it was really just a way to reinforce the own assumptions that they made. It was big garbage in, garbage out. And a lot of these skulls, as some of the historians who've looked at Morton's case have pointed out, we don't know where they actually came from. The documentation for where they came from and who they actually represent, we don't have those things. If somebody sent in a note and said, like, oh, I got this from Egypt. Well, who was it? Was there someone who actually represents an ancient Egyptian, someone who lives there now, somebody of different cultural or other community? We don't have any of that. So the data set is kind of garbage, and it was shunted into these pre-existing boxes. So really, like, even though Morton is sometimes held up as, the objectivist of his age, he didn't theorize, he only took measurements and sort of presented them to the world. That's not really true. He still, made divisions and shunted people into something that's just kind of crud. And even if we, got some ways of measuring skulls that are still used today because of him, and he's kind of held up in the history of science, he's like one of those people that we really shouldn't be looking up to, especially the fact that he knew about all these people using his work to, promote racist views and to promote slavery. And he didn't really say anything about it. And I know this is one of those historical things where, people are the products of their time and all that stuff, but I don't really, buy that. He had an opportunity to, he could have taken the data and interpreted it in a very different way, but really was just used to reinforce the biases that already existed. And that's the really terrifying part of this, is that we're still left with some of this legacy, some of these racist and awful beliefs that still percolate through society and oppress certain groups of people, come from a time in which it was just assumed that, okay, there's just this order to things and I'm going to rank it, and there it is.
And, now, in theory, we know that these racist views are crap. And part of the reason that we know this is actually due to a guy that I was rather surprised I had never heard of before. I've heard of Morton because Morton has a very large skull collection that you can actually go see at the University of Pennsylvania, but I've never heard of this guy. This guy's name is Franz Boas. Can you talk about how he basically showed the skull measurements were not great?
Yeah, so first of all, Boas wasn't necessarily a great hero of science. Like, he kind of started his career by collecting and selling Native American skulls and skeletons in the Pacific Northwest, if I remember correctly. So he was very much, a scientist of his unfortunate age when he started. But at the beginning of the 20th century, he was working in New York, and this was still, American anthropology was still very focused on race and racial divisions and, how to divide people, how traits are passed down. Basically this very much like, we have 5 boxes, you need to fit in one of these boxes kind of view. So at the time that there were huge immigrant communities, moving into, New York City, and Boas decided, okay, like, well, if these categories are real and these traits are basically fixed and passed down the way that we think they're passed down, I should be able to go and look at immigrants of different cultural backgrounds in different countries and their children and see, like, are these traits consistent? Are they different? And the general idea is like that you'd find consistent results, that basically, people who emigrated from, Russia, that their kids would have the same skull measurements as the parents would, and continue so down the line, or, whatever group that you picked, that this would be consistent. Instead, what he found through doing, many, measurements that he and his assistants took, was that there was a large amount of variation. It was very difficult to fit everybody, into, cleanly into these divisions that were thought to exist. And amongst the children, that their skulls didn't necessarily match those that basically wasn't fixed based upon what their parents' skull shapes looked like, or what the measurements were. So, in fact, it showed the variability of the human skeleton, that basically you can't reliably take somebody's skull measurements and say, okay, well, obviously it falls within these parameters. It must be somebody of this race, because when looking at the living people and taking their skulls, like, it starts to get mushy and all over the map. And that Boas basically had to say, like, we can't take skull measurements to divide by divide people into races like this anymore. And unfortunately, nobody really listened to him at the time. Some people even misinterpreted it and thought that, like, oh, well, this means that there's a new American race that's starting to evolve, and clearly we're going to be better, which I can only imagine the headache that he must have had when, that news came down the line. But yeah, I mean, I think part of the reason that, people know Morton better than Boas is it's the way that, the culture of science has changed. That Morton lived during a time where it was very much, the great man of science kind of mythology, that you had the singleton researcher who was a polymath and did a little bit of everything, and they discover something fantastic, and the first person to ever see this thing before, the first person to take this measurement, and there's not a whole lot of competition in the field. By half a century later, like after Morton's death, by the time that Boas is doing his work, you have many more experts, and even at the time, that Boas's conclusions about race were not accepted, that they were basically suppressed by the community, and it really took the atrocities of World War II to get anthropologists to go, like, oh no, like, we really gotten things wrong about race, and this is actually really, really harmful. And then there was much more pressure to change the focus and change, what was thought. And even then, you still had some former Nazi scientists like pushing back and say, oh no, we should keep up the racial programming, and that being published in, popular scientific journals. It's really kind of horrific how long this stuff went on, the inertia of assumptions that always existed.
And it was interesting, it seems, as I mentioned earlier, one of the themes that comes through in this book is kind of the fact that humans interpret skeletons through our own biases. We are looking for patterns, and so we're looking at them through our own cultural lens, usually the lens of white people. And so I was wondering, we're going to keep measuring. We're going to keep looking at human skeletons. We're going to keep finding old human skeletons. We're going to keep studying them and, digging into them and trying to figure out how these people lived their lives, because these skeletons are so informative. But how do we avoid making assumptions? Some of those racist assumptions or, gender assumptions. How do we avoid making assumptions based on the skeletal information that we end up collecting?
That's a really tough one. I mean, if I could solve that answer, I mean, that would give me my chance at the Nobel Prize. I think a lot of it is building a better community and getting better representation within the scientific community, and getting people who are trained as anthropologists and archaeologists involved in the conversation. Some people have already done this. For example, the Navajo Nation has their own archaeology program. They're very active in this point of research, in that it's like, well, these are our people and these are our stories. And, this isn't for, somebody else to kind of, imprint their own version of events on top of this. And it requires conversation and collaboration and being willing to listen. But even, as an individual, saying, okay, I can measure a femur from top to bottom, or the circumference of it, or I can take this measurement on a skull, and that's what the measurement is. It's a fact. But there's always the interplay between fact and theory. Like, fact by itself, or the data by itself, doesn't really tell you anything. It needs an interpretive lens to be understood, to be tested, to have relevance to us. And that's the area in which, that's the point at which we need to start asking, okay, what background am I coming from? Am I interpreting the skeleton in a particular way because, I was raised to believe that only men and women exist and there's no other genders or variation? Or am I interpreting the skeleton a certain way because it needs to be fit into one of these racial categories? I fill it out in a form, like who this person was, and want to know that. I think part of this is the power of saying, I don't know, and saying we're not sure, or I can't tell that, or and that's the stuff that leads us to, like, well, is it possible to test this? How can we get this information, and not just take things for granted? And unfortunately, that's something that requires the culture of science itself to change, and people to say, like, hey, I'm calling this out because I care. I'm not calling this out and saying you should question this or you should question your assumptions because I want you to stop your program entirely. I'm asking you this because I want to understand this clearly. And the more voices and the more perspectives we have on this, the more easily I think that we're going to be able to do this. This is, again, to just reiterate, this is why representation and different viewpoints matter very much, because for so long, as you pointed out, throughout this interview, the story of, people on Earth has been told and written by privileged white men. And as we well know, there's a hell of a lot more variation out there than just that. So the more people we can bring in, I think it's starting to happen now, even ideas of consent. So for example, earlier on you mentioned the damage that's been done to Native American communities and the skeletons that still exist in many museums that are just unidentified Native American remains that we don't know exactly where they came from or who these people were. These are the notes that we have. And in many cases, many of the skeletons aren't being studied and they're not essential to research. There was one particular paper that I read about efforts to repatriate some of these remains, saying a lot of these, nobody comes in to look at these because they don't have good data associated with them. So scientifically, even though they're being kept in museums, they're not always scientifically useful anyway, because we don't know where they came from. But there's an effort to ask and say, what would this person have wanted? Can we tell anything about their cultural affiliation? Can we tell anything about what their desires would have been for their, for their afterlife, basically? And can we do something that's consistent with that? And there's been a greater effort, not only amongst researchers and the Native American community, but there was just a whole bunch of unidentified human remains kept at a museum out here in the Intermountain West. And basically an interfaith group was called in, people representing different religions, to ask advice of what should we do with these? What is a proper burial for these people? That these aren't just objects. They're not just things collecting dust on a shelf. They're the remains of people, and we don't know what their wishes would have been. How can we act respectfully towards them? And we're still very much at the beginnings of this, because for a very long time, there's a quote in plenty of anthropology books, sometimes used, in defense, sometimes used as, pointing out the criticisms that need to be made. Thomas Jefferson quote that the dead have no rights. And that was the view for a very long time. And now, at the beginning of the 21st century, we're finally starting to be well, maybe people do. And we should be respectful of what people would have wanted in life. And, the way that the privileged act about what they want for what happens to them after death, we should extend that courtesy and that consideration to other people as well. So we're just starting to do that. And I'd like to see more of it. And the more perspectives that we have in the mix and the more vigorous the conversation, I think the better off we're going to be.
Well, Brian, thank you so much for picking bones with us.
That was perfect. Thank you so much.
You can learn more about Brian Switek and his new book, Skeleton Keys, The Secret Life of Bone, at scienceforthepeople.ca. While you're there, follow us on Facebook or Twitter. Better yet, kick us a few bucks on Patreon and get this year's scientist birthday card and other bonus goodies. If you're feeling especially friendly, leave us a review on iTunes. It really does make a difference. Thanks for listening, and we'll see you next week on Science for the People. Fabulous. Thank you.
All right, great. Yeah, I'm glad that we had plenty of room to, not chew the fat, because we're talking about osteology, but
Pick the bones. Pick the bones. How many bone puns did you come up with?
Well, I used them all up for the chapter titles.
Oh, there were some good ones. Actually, I think my favorite was when you decided that without Jaws, the movie Jaws would have had to be renamed Whole.
Yeah. Or pharyngeal sled. I like that.
No, I just like Hole.
Hole, yeah.
Isn't there a band called Hole?
Yep.
Wasn't Courtney Love in it?
Yeah, it's just Courtney Love biting people for an hour and a half.
But she wouldn't be biting people. She doesn't have any jaws. To give you a little background on this science and spirits thing, I'm going to stop this recording. Okay.
Science for the People is produced by Rochelle Saunders and edited by Ryan Bromsgrove. Helen Quivalon is our publishing liaison. We get research help from Josh Witten and consulting support from Desiree Schell. Our frequently seen guest hosts are Marion Kilgour, Anika Hazra, and Jessica Yaros. Our theme song is called Binary Consequence, and it was written and recorded by Fractal Pattern. Science for the People is entirely listener-supported. You can find us on Patreon, where you can support us with monthly donations in any amount, or you can send us a one-time donation in any amount via the donate page of our website. Science for the People is created in partnership with the Skepchick Network. a collection of blogs, podcasts, and video content focusing on the intersection of science, popular culture, politics, and social justice. You can find out more about Skepchick at skepchick.org. The show is hosted by science news writer Bethany Brookshire and me, Rochelle Saunders.